Welcome to another CO2 Monday and the Refrigeration Mentor podcast. Once again, I want to thank everyone for taking the time to come each week to hang out with us, listen to the experts on CO2 from around the world. And this week, we have two very smart and well-educated on CO2 gentlemen, Joe and Peter from Emerson. We're diving into Copeland Stream Compressors. What I'm really excited about today and this conversation that I know a lot about Copeland. I worked for them for many, many years. And now I want to pick Peter's brain because Peter's been the guy who've been testing these. He's been working on them and seeing what he did to them. They put a lot. I've even seen it on the scroll compressor, but I'm excited to see what the CO2 has been done and how it evolved because he's been doing it for over 8 years. And Joe is an expert at research and development. I believe he's been newly acquired to Emerson, and I'm excited to get into this. So if you got questions, please put it in the chat. Joe and Peter, welcome to the Refrigeration Mentor podcast. How you doing?
Hello, good afternoon. I'm doing well. How are you?
Fantastic. Peter, why don't we start off and you do an introduction, then we'll get Joe to do an introduction about a little bit about your background and involvement with CO2.
So I initially graduated from a Czech university, technical university in Brno, as an HVAC engineer. And just after that, I joined a Czech company, a small size company, which was producing industrial refrigeration machines. So it was mainly about ammonia, but also about HFC refrigerants and all this stuff, large compressors, oil management systems for those, and so on. And 9 years ago, I joined Emerson. So after 10 years in the previous company, I joined Emerson as a development engineer working on reciprocating compressors. And from a big portion at the time, it was also CO2 Stream family, which was being developed at Emerson, like step by step in different platforms. And after 3 years on that position, I moved to the position of manager of the engineering of reciprocating compressors. And I used to work on that position for 6 years. Nowadays, I am responsible for the engineering laboratory in Mikulov, Czech Republic, at Emerson facility.
Awesome. Super. Thank you so much. Really appreciate it. Joe.
Hey, thank you, Trevor. Thank you for the opportunity to talk about the CO2 in this great meeting. My name is Joe. I'm a CO2 system engineer with Emerson. I just joined this company in this middle of May. My career life starting at 2009, right after I got PhD in China. And after that, I worked for a university in China, doing teaching and the research things for about 7 years. Then I found myself, my passion really is that the real system I would like to play with, to see the system running instead of really put it on the paper and in the model. So after 7 years teaching and the research, I joined a small company called Creative Thermal Solution. The founder, whose name is Petr Chadima, who is really the real expert of this industry, brought me into US and joined his company called Creative Thermal Solution. I worked at the called CTS for about 7 years. Run a lot from that company. I have worked on all different kinds of refrigeration projects, including like sensors, A2Ls, coil design, system design, all kinds of things. And just this year, I decided to move one step closer to the real system, to the real market. So I took the position for the system engineer of Emerson. And fortunately, the prefix of this position is started with CO2, so which means still a lot of develop and innovation be included. So I still found a good fit to put my experience with some development and theoretical things. So yeah. Thank you very much for the opportunity. If I unfortunately make this podcast become a little bit like a classroom feeling, I apologize in advance.
Oh, don't. This is awesome. I thank you, and I'm super excited about this conversation, and there's a lot of knowledge here. And we're let's just dive right into it because I know we want to really. I want to get a lot of the questions, and I really appreciate the slides that you bring up. So during the podcast, I'll walk people through that are listening to this down the road and of the slides. But if you guys want to go ahead and share it, because I'm excited to dive into this. This is real exciting. Awesome.
Sure.
Yeah, I can see everything.
Okay. So
So
Peter, you want to start? Yep.
I can start, yes. So at the beginning, let's introduce the family of the CO2 reciprocating compressors, Copeland. So actually, what we have today is the family of the compressors, which is covering the range from 30 to 50 horsepower motor models in both transcritical and subcritical versions. So here we can see that we have 9 different displacements. This is covering the majority of the needs in commercial refrigerations today. Initially, the compressors were started being developed in Europe, but it was very close cooperation between European and US Copeland development centers. So at the same time, all the features and the safety precautions were also took into account for both markets, European and American one. So the compressors are UL approved today, and they are produced in different options and versions. But all of those 9 displacement models, they have common footprint. So all compressors can be fit on the same feet size. What makes the life easier for the OEMs with preparation of their frames. The compressors are developed in I would say Copeland standard. So I think that it's also very well known on both continents that this is super standard for the commercial refrigeration. And the main difference between HFC and CO2 compressors is definitely the pressure which the CO2 compressors withstand, and also related kind of massiveness of the design as such. When we were doing the development, one of the deep focus was also on the level of sound and pulsations and vibrations which the compressor should have in the field. On the discharge of the compressor, you can see there is a big plenum which helps to decrease the level of pulsations and also the sound of the compressor. And it also helps to not to influence the suction part of the compressors much by the temperature of the discharge gas.
So Peter, I do have a couple questions already. So when you were involved in some of these testings, and the high and low side design pressure, I see it's 1958 and 1305, so 135 bar and 90 bar. So would you guys actually test up to like 2,000 pounds to see what would happen, or 3,000, 4,000? Because I see the burst pressure says 6,992 and then 420. So what actually was that test? You just filled it up and see it, and then all of a sudden it would start to leak at the seals, or when you're doing these burst tests?
Yeah, well, so actually there are three levels of the pressure safety in the compressor. So the first of them, and as it is also shown on this overview, is the maximum operating pressure. So that is really the maximum pressure at which the compressor can work continuously without harming the efficiency, without harming the lifetime of the compressor. So all the components mechanically are designed for this maximum pressures.
So, okay, that's perfect. So anyone who's listening, the maximum pressures for different ranges is 1740 PSI or 120 bar. So there's a lot of people are like, oh, I'm really worried about the pressures and how high it can get. But the compressor, you just said that it can work and function at 1740. So the 4MTLS 40 KE for an example. So designed to run at those pressures. So that's good to know. So like, understand. Awesome.
And so this is the first important pressure limit. The second one is this 1955 psi, 135 bar. What is the design pressure or the maximum allowable pressure in the high pressure side of the compressor? And that's actually the limit on which the pressure relief valve is set. And it is the limit up to which the ceiling of the compressor is designed, and it's guaranteed that it will withstand this pressure without any leak.
Okay,
but it's still very far from the maximum pressure which the body can withstand. And that was initially your question. So it is then the berth pressure for which all the components are designed in terms that they have to withstand this pressure without any leak, without any burst.
Yeah.
So when we do the development of the compressor, this is the pressure on which each of the component is tested in each of the development step. And at the end, before the product and the compressor is released into serial production, there is certification testing. So we take all the components and we test them with high pressure oil up to this 420 or 330 psi bar on high side and low side, and all those components withstand this pressure without burst. And several samples are tested and so on. So this is
okay. So you'd make a batch of them, for example, and you'll pick just random ones and do that test. Awesome. That's super cool to know. And this is what people don't really understand of the quality control that the manufacturers like Copeland does, is to make sure that they can randomly test. And because I've been to a lot of the factories, and man, the quality control is amazing, which I love. And it's nice to see that there are layers of protection, just so everyone understands. Yes, CO2 is a higher working pressure, but the components are designed for these pressures.
Yeah. So at the end, if it happens in the field that the pressure rises up above 120, it is still safe. It is no risk in terms of safety. There is a risk in terms of the reliability of the compressor and the correct function only, if I can say only.
Yeah. Yeah, no, that's awesome. I love that. Okay, let's keep going. Oh, and the relief valve that's on it, is that UL? You need it on every one, the discharge one.
You need to have it on the discharge of each of the compressor, and it's delivered together with the compressor from our side.
And do you guys recommend replacing that if it opens up? Because I know some people say yes, replace it. No, or
yeah, definitely it's recommended.
Okay. Awesome.
The pressure is the valve is using a spring, but it happens very often when you have a leak that the sealing is not 100%, and after some time you can see a leak again. So we always recommend to replace this PRV whenever it opens in the field.
Awesome, thank you.
Yeah. So that are the high pressure relief valves. The compressors are also delivered with both suction and discharge service valve. Customers can choose from various motor versions for both 50 and 60 hertz network. The compressors can run with variable speed.
So what's the difference in the motor versions now? So you're saying that there's motor versions. So it's a 50 hertz motor version and a 60 hertz motor version, or is there different motors for those different hertz range? What's that mean?
Actually, the basic motor, which is designated FSD in our nomenclature, it's motor version which is suitable for both speeds. For 50 hertz, it is in relation to the 400 volt voltage. For 60 hertz, it's 460, 460 volts. And then there are also other motor versions, also for 575 volts, 60 hertz, and
Canada. Thank you.
It's there. Awesome. It's there from the beginning.
Awesome.
And the compressors, as all the other compressors from Copeland, the newest families, they are delivered with Copeland compressor electronics, formerly known as Coresense. There are more versions of this protection, and it also is a little bit different between Europe and the US.
Yeah.
So in Europe, in the last
Unfortunately.
3 years, yeah, there was some new development in Europe. So there is a new Copeland compressor electronics module, which is more modular, and it also gives you better connectivity.
Yeah, I seen it.
So
It looks
there
awesome.
is Bluetooth
That one looks
and so
awesome in
on.
Europe.
So, and I think it's only a matter of time and the interest from customers if it will be one day implemented in America as well.
Yeah, the big thing about Coresense, like when I worked at Copeland, I could see it was ahead of its time. Like these electronics were built 15 years ago for compressors, and it took a long time to get where it is today. So love hearing that. Quick question too. You said 50 horsepower. I know that's been in development for many years. Is there actually 50 horsepower compressors in the field right now running?
There are definitely some
Okay.
running in the
Awesome.
field.
Great.
So there is still some kind of ramp up in this largest model, but they are available, and it's up to the agreement with also local Emerson sales representatives to get it.
Good. Excellent. Let's keep going. I know I'll start talking and we'll just keep keep going on one section.
Stop me when you want to stop me. But I will not be much longer on this slide. So as I said at the beginning, there is this LT or subcritical, if you want, version. So actually it's mainly about the optimization of the motors. So it's working at the optimum efficiency with the lower loads, which are coming from the low suction pressures and so on. So, and those low subcritical versions are for the smaller displacements up to this 765 cubic feet displacement.
Yeah, fantastic. Love
And
that.
here on the right bottom, you can see the examples of the operating maps. So you can see that the maximum pressures and also on the suction, you can go actually up to nearly 50 bar. And sorry that I'm mentioning so many bars and
That's
degree
okay.
C.
That's perfect.
That's why I am so. That's
This is
because I am
perfect.
used to talk in this. But there are always also PSI and Fahrenheit mentioned on the slides to make it easier for both sides.
No, I think more people need to understand that. That's a good point. Like more people need to understand both terms. So even even you understand the PSI, I need to understand the bar because it's important to understand these units because this is a global community and we're gonna see more and more of these different units. So, but that this is really good point is for the people that are listening is that every compressor has an operation envelope. You need to run that compressor in that envelope for it to last that 15-year life cycle, 20-year life cycle. And this goes for any compressor manufacturer. You need to stay inside that operation envelope, look it up, find it, and make sure that you're always in that envelope while you're running.
And people are also asking what happens if I'm out. And as you said, you can damage some of the part in the compressor. You can shorten the lifetime. But what I want to point out is that always that is not only one effect. If you go, for example, to the left below the minimum suction pressures, you increase the compression ratios. You have extremely high discharge temperatures, and you will also influence the lubrication system.
Yeah.
And many effects, many other effects. And this is one of the probably topic for one of the future slide that we can more talk about what is happening if we go above some of the line which you see in the envelope on the picture.
Yeah, we'll dive into that. We need 3 hours here, not an hour.
Okay, so if there are no questions for the lineup, we can go to another slide.
So Peter talked about the compressor, and Travis have a lot of questions about the high pressure. Yes, for CO2, high pressure is the first thing jump into our mind. I remember like 5-6 years ago when I first started developing a CO2 unit, it's really difficult to find all the components can working at that high pressure. We have multiple of accidents. So safety become the biggest issue at that time. But after 5 years, you can see right now, you can find the oil separator, valves, filters, side glass, pipings, everything can work at 120 bar, which is awesome. Really, the entire industry is developing. So as a system engineer, I would like to talk about a little bit of the high pressure hazardous mitigation at the system level. Same as Peter just mentioned, for the system level, I think we also have 3 different like safety setup to mitigate the pressure thing. First is the maximum allowable set point. Similar as the working envelope of the compressor, you will have to control the system to running at the allowable pressure or the desired pressure. One very unique characteristic for the CO2 system is whatever you control, if it's running at the transcritical mode, let's say, put this way, it is different with the HFC system. You will have no superheat or subcooling to control with. You have to go with direct pressure control. So this chart on the top right side is the pressure line with the temperature at the gas cooler outlet. So when running at the transcritical mode, the pressures usually become a function of the temperature. And as temperature going up, the optimized pressure will just follow up. But we will have to limit it to at some point. Don't make it running beyond the working envelope or some limitation of the weakest component. We don't want to trust anything, right? And really the reason why CO2 have to follow the optimized pressure, well, I make it a little bit like classroom. I put the cycle on the pH diagram. So say we have the gas cooler outlet temperature at a 95 degree, highlighted with the thicker red line on isothermal curve on the chart. So if we push the pressure at just slightly above 1000 psi, and you can see the cycle, it's the blue line cycle, and we have only just a teeny tiny delta H at the evaporator. The inlet quality of the coil become 0.9, which is majority of the thing is vapor. Vapor really didn't provide you too much capacity, but you still need to compress it from 0.1 to 0.2 L, consume a lot of compression power. So the efficiency is pretty low. It's even less than 1 in terms of COP. Well, if we push a little bit higher pressure, you can see on the chart, if we push from 3L, 0.3 L to 0.3, then we gain a lot of delta H.
Yeah.
The
much more
quality,
capacity.
yeah, that's a lot of capacity. So we gain the quality changing from inlet quality changing from 0.9 to 0.5. That's a lot of gain. But we just need to push to add a little bit of compressor power. So that's the delta W. So that's really means if we're running at a too low pressure, efficiency is bad. You have to push it higher. But if you keep on pushing it higher, yes, you get a little bit more capacity, but you need to spend a whole lot of compressing power. But then the efficiency started dropping. So which means we will always have optimized the efficiency in terms of the pressure. So if we plot everything together, we get a bunch of these curves. So say this is the gas cooler outlet pressure, and this is the efficiency. And you can see for the temperature at, let's say, 85 degree, you need to push the pressure all the way to like 1100 PSI to get it optimize the pressure. If you push more, the efficiency started dropping. And for higher temperature, the peak efficiency happens at a higher pressure. And fortunately, as Peter mentioned, our compressor can do at 120 bar or 1740 PSI, which is somewhere here. So you can see it covers the majority of the temperature. Only thing missing is like 120. We may still a little bit behind the maximum efficiency, but since in the temperature being 120 is extremely hot, then they take too much percentage. So I think if we limited the system to running at 120 as the maximum allowable pressure, it shouldn't hurt the efficiency too much. So really that's give us a very good opportunity to make the whole system running at a fairly good efficiency.
Yeah, and so this would be all done in that high pressure controller, I would assume, because I know most of the controllers and manufacturers, what they're doing is that using that ambient sensor outdoors, wherever that is, to try to get that best COP, like you're talking about. You don't want to not go up high, or you don't want to go too high because you don't get enough, too much work on the compressor for little capacity, or you don't want to go too low because you don't get enough capacity for the amount of work you're putting in. So that's where that COP or the algorithm built into those high pressure controllers.
Yeah, exactly. Yeah. But keep in mind that the number of the pressure or the function of this curve, it changes with different suction pressure. If you're opting for AC system, the curve may look different a little bit versus the refrigeration, medium temp or low temp. It might get a little bit different.
Yeah.
But anyway, that's the first, well, in terms of the control, it's also a safety chain. The first level of the safety chain has a maximum allowable pressure setting in the controller. When system is running, never have a chance. If it's operate normally, it never have a chance to beyond that maximum pressure. But since not always running as we want, right? Sometimes we lost the control. And the second level is our high pressure switch. It is similar as what we have seen at the HFC system, but I would say for the CO2 system, it's a little bit more important. Not just to cut off the compressor when the system is running to be too high pressure, but it also can help to simplify the entire control. For example, for a booster system, you will have a flash tank. Usually, flash tank has a lot of refrigerant inside. It become a very crucial point to protect. And let's say when the pressure of the flash tank keep on increasing, the reason why it will increase is, so looking into the mass balance point of view, the refrigerant sent to the flash tank through the high pressure valve, and the extra vapor being taken out to the suction of the compressor through either the bypass valve or the suction line. Those mass balance keep the pressure of the flash tank stay at the constant point. But if something happened, the inlet mass of vapor is more than the taking out, then the pressure of the flash tank keep on increasing. And the way to do that, either you can suddenly cut off the compressor, but at that time, you don't have the vapor descending to the flash tank. That's true, but you also don't lose the mass taking out to the compressor. Then it's not a very fast response to reduce the pressure. So the way with the high pressure switch installed, the way we can do is to close the high pressure valve. In that way, we reduce the amount of mass sending to the flash tank, but we keep on taking vapor out from the flash tank. Then the pressure of the flash tank can very fast reduce. But of course, then you risk the high side pressure. Yeah. Fortunately, we have the high pressure switch installed. It will delay the cutoff a little bit, make sure the flash tank pressure go down first, then cut off the entire system, make the whole system a little bit more safer.
Yeah, so, and that's a big thing that I talk about with technicians too, is like, if you're running really high pressure, you can always go and shut down a couple compressors to reduce that, because those compressors are causing the pressure. They're increasing that pressure, and that's what these high pressure components or switches are going to do. It's going to cut off those compressors. So if the maximum pressure, working pressure is 1740 psi or 120 bar, what is the type of high pressure switch? What should those limits be set for?
What I have seen from the field, usually people will set it like 3 to 6 bar below the maximum working pressure, or not working, design pressure.
Okay.
Yeah.
Perfect.
All right, then the last part, if what's come towards the worst case scenario, it will go the pressure relief valve, pretty much as same as the HFC system. We would like to avoid that thing to happen as much as possible.
Yep.
And the other unique thing or special thing for the CO2 system is the standstill pressure. For that HFC, when system is stopped, you don't have need to worry about the pressure at all. But for CO2, especially for retrofit system, if you have the display case or the coil designed for lower pressure but retrofit to be CO2, when system is stopped, the standstill pressure, it could be way over the maximum design pressure of the coil. So from this point of view, we need to keep the pressure low for the entire system when system is not operating. One thing I have seen a lot of people, more and more people is put into the system is the accelerated condensing unit or backup condensing unit.
Yep.
When the system is not operating, you utilize that condensing unit to pull down the flash tank pressure, condense more vapor into the liquid to keep the pressure low. And also need to go through the pump down procedure when it's planned stop. Then utilize the isolated valve to stop everything to protect the low side from the high pressure. So I would put this way. So for the flash tank, for the backup condensing unit is quite often to be seen on the larger system, but for a smaller system like the condensing unit for the working coolers, may not necessary to put an additional condensing unit.
Yeah.
Isolated valve should be good enough. Like I put on the chart on the right corner. If you have the condensing unit that can do 90 bar, which is above the standstill pressure, as long as when the system is stopped, as long as you can cut off these two isolated valve and isolate the working the unit cooler, separate the unit cooler from the entire unit. Since the coil sits in a relatively lower environment, the pressure should maintain low for a fairly long time.
Yeah, makes sense.
So it won't be a problem. Yeah, but again, the third level will be the relief pressure, especially on the low temperature coil. Okay, back to you, Peter.
You're muted.
So the next topic can be talking about superheat control. So I would start with the reasons why this is so important for the compressor as such. And then Joe will take over and he will talk about how to control it in the system and how it can be handled. So from my perspective as a compressor developer, I would say for the low superheat, there are several things which can happen if we have too low superheat. It has been said several times for the empty refrigeration systems for CO2, the minimum recommended superheat is 10K or 18 Fahrenheit. For the low temperature system or subcritical system, it's quite higher, so it's 20K or 36 Fahrenheit. And if it is higher, if it is a little bit higher, it's definitely good. And how close to this low limits is the let's say control system setup. It also depends on the quality of the control and the size of the system, because in each of the system it can fluctuate in different way. So that's up to the also experience of the OEM and the people who are putting together the design of the system.
Yeah, most of the times I see, Peter, the manufacturer of the equipment has usually a higher superheat for their systems that they're looking for. So for an example, you're saying you would like to see 20K, and they'd say 25K for an example. So I've seen a lot of that, or 10K, and they'll say 18K. So I've seen that a lot.
Yeah, that's definitely completely fine. But on the second half of the slides, I will talk also about the fact that we don't want to have too high superheat. But if we don't have, if we have the low superheat in general, what's happening in the compressor? The most important effect is that the lower the superheat is, the more oil is diluted, the more CO2 is diluted into the oil. What decreases the viscosity of the oil, and it simply leads to a bad lubrication in the compressor, and usually to excessive wear of the components, bearings, piston rings, and whatever what is really moving in the compressor. I have on the right hand of the slide, I have this solubility chart, and I will talk about that later on because I have one example with real numbers, which are based on our measurement in during the testing phase. So, but still on the left, you can see the example from some of our testing, because during the development phase, we always test the limits of the compressors, and we very often break the compressors. We often break the parts to see really where the limit is.
Love it.
So here is one of the example. It's not broken, but you can see on the left top, the two pictures. That is the wrist pin from one of the CO2 compressor, and the small conrod bearing, which is heavily worn. So in most of the compressors and in our compressors, the bearings which are in the CO2 compressors are composite bearings with typically a PTFE layer on the contact surface. That's simply because they have perfect properties in terms of the contact pressures they can withstand, and also how they behave in the situation when there is a poor lubrication in the bearing.
Okay, I like this. So
yeah.
so the wrist pin, so everyone knows you get the piston, then you have the rod, and the wrist pin is what holds those two together. And I can
Yeah.
actually see in those rods in the CO2, is there a hole drilled up to it in the journal that it goes right up to the wrist pin, so you have oil always going up to that wrist pin? Because
If
some have it and
yeah.
some don't. So
Yeah,
they do in this.
if you have the compressor with the oil pump, then typically yes, you will have the hole in the full conrod, and it's leading to the upper bearing, and there is the oil delivered directly into the bearing. But for many of the compressors, mainly with smaller displacements, smaller sizes and smaller dimensions, there is no oil pump, but there is splasher, which is rotating together. There's a plate on the end of the shaft, which is rotating together with the shaft, and it is touching the oil level and throwing the small oil droplets into the crankcase, and it's lubricating all the surfaces, and it's also reaching up to the upper bearing in the connecting rod. So there, in those compressors with splasher, you will not see the holes in the connecting rod, because
Okay,
it doesn't make sense. We don't have the oil pump there.
yeah, so this is a really good point. So if you're running that low superheat, which is actually you have superheat, which we'll say we got, for the example, we got 5K superheat or 10 degrees superheat, but that's too low because that oil is very soluble. It has a lot of CO2 in it. So as it's going through the compressor, it's washing the oil away, causing
Yeah.
friction, causing damage. Now, for this example that you have the wrist pin damage, would it be a case where you take off the head, so you pump it down safely, you get all the refrigerant out safely, electrically isolated, but you take the head off, and would this be a case where you would turn the crankshaft up and push on the piston, and it could drop potentially?
Yeah, it's the extreme case when you get the ovality in this bearing. It can happen, and it happens really if you really completely damage this upper bearing in the connecting rod.
Because
It's not so often in the CO2 compressor, because here you have the bearing and you don't typically reach this huge ovality, but still you remove the sliding surfaces from the bearing, and there is more and more friction, and it's typically it can typically happen that the wrist pin gets stuck into the
Jesus.
small eye bearing, and you destroy the piston.
Yeah, so it seizes up, and yeah, okay, that's a good point.
In,
So in
in
HS,
HSC,
Yeah, an
Sorry,
HFC,
go
sorry,
on.
Peter. So an HFC compressor, I know when you have a lot of flood back, the first bearings, that the main bearing that goes, the main bearings one goes. So we've always done something called shake hands with the crankshaft. So you take off the pump, and if you got a lot of up and down play, that is flood back with HFC system. On the CO2 system, if you have a lot of flood back, is that a test that you would also do similar to check that main bearing?
This is the test. What we do with typically some percent of the liquid coming back into the suction. So it's long-term test when we test at this condition. And Joe, if I may ask you to click 2 times, I will show you this example. So here, the solubility chart, I don't know how many people are familiar with that. So it's showing decars of the pressure, which stands here for the saturated vapor pressure in the refrigerant. Here on the bottom X line, we have the temperature of the oil. And on the left, on the vertical line, we have the kinematic viscosity of the mixture of the oil with CO2 in this case. And if you collect if you measure the data in the temperature in the crankcase and also the pressure in the crankcase, you can see how the viscosity behaves. And it is the influence of the diluted CO2 in the oil bath in the crankcase. So you can see we have these two lines. One of them is green, and it is a normal rating condition. So it's with the recommended superheat 10K, and we are running the condition at 14 Fahrenheit suction pressure or saturated temperature at the suction, 1305 psi on discharge, and 95 degree Fahrenheit return gas temperature, or the gas cooler temperature. And if we run with this at this condition with the recommended 10K superheat, we typically reach discharge temperature around 230 Fahrenheit. The crankcase oil temperature is around 120 Fahrenheit, and everything is fine. And you can see that the kinematic viscosity is around 10 centistokes with our POV 68 oil, which is typically filled into the compressor. And it is still fine, and the compressors easily survive long-term testing. And really, with that, you can be fine. But we were running the test with the 10% of liquid in the suction, and that is and the influence of that liquid is doing several things. You go down with the discharge temperature. You can see that the measured discharge temperature was around 185 Fahrenheit. You absolutely decrease the temperature of the oil in the crankcase. You can see it's 21 Fahrenheit.
Yeah.
So it's crazy low. And by this, there is much more CO2 diluted in the oil. So you can see that the calculated ratio is like 40% of the oil bath is actually CO2.
Wow.
And then the kinematic viscosity is around 2 centistokes, what is 5 times slower. And this is based on this. Yeah, and the lubrication is poor, so the oil loses nearly all the viscosity, and with this you can easily damage the compressor similar way what you could see on the pictures on the left. And I can tell you that this calculation and the viscosity calculated is based on this solubility chart from Shrive, what is the producer of the oil. And actually, when we did some other measurements internally in Copeland, we found out that with this condition, the oil viscosity goes even below 1 at some cases. Wow. So that's nothing. So we have like water in the compressor, and you are trying to lubricate the bearings with it.
Yeah,
So, so
that's why this is why superheat is so important, and you really need to
yeah.
understand it. And so this is like 10% liquid added. So would a minimum discharge temperature in the programming help? Because I know that you need a lot of factors. So you need the oil temperature here, you need the discharge temperature and your superheat. But could that be a kind of a test? Like, have you ever just test to see how if that discharge starts to get really low, that could be causing it. You should be concerned about that as well. Is that right?
But actually, from yeah, I see, but I would say it in a little bit different words. Uh, what in my understanding is happening when you have too low discharge superheat, you have a lot of CO2 diluted in the oil which is thrown out from the compressor. It goes to the separator, and you still have like nearly even 50 to 50 ratio CO2 and oil in the separator, and you are injecting it back to the compressor. So this is really bad. You want to have this higher discharge superheat, and I don't have the number
Yeah.
now
Yeah. It does.
now in head, but it definitely should be even much higher than the suction superheat, probably 30 40 Kelvin.
Yeah, because this is something
So
I didn't. We don't use. Well, when I worked at Copeland here, we did not use discharge superheat. But I know competitive manufacturer Bitzer, they use discharge superheat. But I don't know in Europe, do you guys use discharge superheat as well on your compressors when you get you testing? Like the technicians would check that, or no? Do you guys recommend doing that check?
we do follow the discharge temperatures, which should for each of the condition be in
Yeah,
some range based
yeah.
of the previous testing and the ideal case. But
Always check the
I
discharge
don't have now.
temperature
Yeah, yeah. You should check it. You should check it.
every time.
Use the pH diagram. Is the
Yeah.
easiest and perfect tool for really quick check how far you are from the line with saturated gas, and you on the discharge you definitely want to have 20 40 30 Kelvin from that line.
And
so,
this is
so
what's the crazy thing about CO2 is that you need to have make sure you have superheat, but you also need to make sure you don't run too hot, which is your next
yeah.
point on in too high of superheat. So
And that's something what also you need to check. It's mainly coming to the operating limits of the compressor, so and also the efficiency. So if the suction superheat is too high, and I am now speaking about probably 40K in the superheat, it will increase the discharge temperature heavily, and it influences directly the motor efficiency, because the motor in our semi-hermetic compressors is actively cooled down by the suction gas. And if you don't give this cooling to the motor in a proper way, it's running hot. It at some extreme conditions can trip on the motor winding. There is a protection in the compressor, but you can see the tripping, and several cases are that people are coming back that something is wrong with the motor. No, it's it's typically the case
I've seen it
that
so
you are
much.
running too hot.
Yeah.
And another thing is that you are really limiting the map, operating map. So what can be seen on the picture below is the orange line and the pink line. So the pink line is the operating map with the recommended 10K superheat. So you can see how high you get with the discharge pressure in the high compression area. If you have 20K, so it's double, you can expect the limitation shown in the orange line. So you are really limiting the operating area, and especially at the start of the system, or when you are running hot on discharge, it can lead to the tripping of the compressor based on the too high discharge temperature.
Yeah, and I love that. This is why it's so important to understand the compressors itself, because now that operation envelope means a lot. Because all of a sudden, if you get up into that zone where you need to have cooler suction gas, so lower superheat, you may have to involve other components like liquid injection or some sort of injection to cool that compressor down. And that's what I've been seeing with manufacturers designing some equipment to help the compressors last longer when things do go awry.
Yeah.
Awesome.
There is one question in the chat. I don't know if you want to answer it now or leave it for
If
later.
you want, if you, I can read it out. So the question is, what happens to the compressor crankcase or temperature with a long compressor runtime of 10K superheat? Example, the low temperature supermarket application often will have a lead compressor on a variable speed or variable capacity compressor. This compressor will rarely shut off. Does the oil temperature start to drop from 50C after a certain amount of time?
No, if you no, if I understand it correctly, if you keep this 10K superheat permanent, you don't go down with the superheat, and you are running at the same condition. Actually, the temperature in the crankcase is controlled by the suction temperature and the superheat, and also by the temperature of the oil you are returning back from the system and from the separator. So if you are running on the steady condition, I wouldn't expect that the oil temperature would start dropping.
Okay. Awesome. So
So that are only some of the examples.
love it.
I really recommend people to find out and find these diagrams if you are into the designing of the system or if you are doing the maintenance. Both this solubility chart, which is released by each of the oil producer, and also the pH diagram. That are the things which our technicians in the laboratory use daily, because it's very simple, very quick, and it's really illustrating the situation without doing any calculation. And it will quickly tell you what can happen if you continue running at the condition where you are not sure if it is correct or not.
Okay, I do have a question about the oil, which is very important because you guys use POE 68, other manufacturers use 85. And I see here in North America, there's multiple occasions where there's Bitzer compressors and Copeland compressors, and they're all running at with 85 in it, and they seem to be running fine. What's your guys' recommendation in Europe for those occasions if that happens? Should they all go with 68, or should they? It's always better to go with 68, but have you guys tested it with 85 and did it reduce the life of it?
I think in general there are, as you said, some cases where you cannot avoid this. We have done some limited testing with higher viscosity oils as well. It typically doesn't harm, and you should also always discuss it and consult it with the application engineers from Copeland.
Yeah.
Because it can be case by case, and it always needs to be confirmed by our application engineers.
Yeah.
Because it's not typically released oil for the compressors. There is also another alternative. It is also 68 centistokes oil, but it's PAG. So it's a different chemistry, but the same base viscosity. And that compressor oil is showing a little bit lower solubility of the CO2 in that, but it's not very significant. And both oils have been fully tested by Copeland, and they are qualified.
Perfect. So make sure you follow up with the manufacturer, follow up with the Copeland as well if this is the case at one of your applications, because I know I've been asked this so many times. But make sure you're following up with the manufacturer because they're the ones that have done these tests. And so at the end of the day, it's your responsibility to check that stuff out.
Yeah.
So I appreciate you answering that. Thank you.
Probably one small warning or important note: if you are changing the oil from POE to PAG in some case, I don't know why people can do it sometimes, and we have been asked if there is a modification to the system and somebody wants to change the oil from POE to PAG or vice versa. you need to flush the system very well, because those two compressor oils, they don't like each other. I mean PAG and POE, and it can lead to excessive foaming. It can lead to oil degradation. So if something like this happens and you need to do it, you need to flush the system several times.
Okay. Yeah, I've never heard of that, but thank you for pointing that out. Let's keep going.
So I think we can move. This is just the last visualization of the state of the oil and the low viscosity. So we can go to another slide.
Okay. So Peter talked about how important the superheat is to protect the compressor and make it running reliable. And from the system point of view, there are a bunch of ways to manage the superheat. For CO2 system, it's a little bit different with the HFC. Usually, for HFC, we don't worry too much about the high superheat and big concern of the low superheat. But for CO2, especially for the booster system, since you have the low temperature compressor discharge the very hot gas directly to the section of the medium temp, if the ratio is not correct or something control is wrong, then you will have to have a fairly high superheat at the section of the medium temperature, then cause a lot of high discharge issues, as Peter just went through. Of course, the easiest way to mitigate the high superheat issue is to utilize the liquid injection method, as we usually see a typical system. But for the CO2 system with the flash tank, when the flash tank pressure running at a similar pressure, same pressure as the section of a medium section, it might not be a feasible option. You will have to find a different location for the liquid injection. But the liquid injection is still a major way to mitigate the problem. And the other way for the CO2 system is to put a heat exchanger between the supply line and the return line, as I show on the slide, is to plate the heat exchanger. Then you can utilize the relatively warmer refrigerant from the flash tank to either cool down or warm up the suction line back from the cases to maintain the temperature at the same level, thus maintain the superheat. It can work for both low superheat and high superheat scenario. And the other version of the supply return heat exchanger is to put this heat exchanger directly into the flash tank, this so-called flash tank inline heat exchanger. So say if we have a flooded liquid flooded back from the case, and sending the two-phase refrigerant into the flash tank. Since the flash tank running at a relatively higher pressure or temperature, then they can help to heat up and vaporize all the liquid out. But then the additional cooling can help have more liquid in the flash tank, which you get the superheat, but you don't necessarily to waste any efficiency. So it's also a good way.
So for the liquid injection, I think I've read somewhere it's 250 degrees Fahrenheit maximum discharge temperature. Is that correct? 250?
Yeah, 250 is usually the threshold to activate the liquid injection. As Peter mentioned before.
That's when it should be activated at 250, because I know 6 inches down the discharge line, you should check it. If it's 250 or above, that's bad. You're running too hot. Is that when, or is there a range on when you should start injecting that, or is that up to the manufacturer of the equipment?
That is the most of the system do, but I'm not a guarantee 100% of the unit will do that way.
Yeah, because you're always running hotter in the head, and then if you check 250, you don't want to start if it's getting up to 300, 6 inches down. We know that oil's starting to lose lubrication and starting to break down. So hopefully you're injecting before that. So okay, so and that's up to the manufacturer of the equipment, I'm presuming.
I would say so.
Okay.
Yeah. And for the low superheated control, usually for the HFC system, people rely on the suction accumulator. Here's one thing I want to point out is for a system with a larger flash tank, you have tons of liquid installed in the flash tank. And usually the suction accumulator has less volume than compared with the flush tank. So which means the liquid in the flush tank is sufficient to fulfill the accumulator. So that way, if you keep on have two-phase, have liquid sent into the accumulator, eventually will end up with flood the compressor. So it may not be the best option for the CO2 system with a larger flush tank.
That's good to know.
Yep.
You guys want to keep going for a little bit and finish up these slides? Are you guys okay with that, or?
Completely okay.
Okay.
Yeah, so the last slide is talking about the oil management. Since the superheat control is related to the oil, and one characteristic of the CO2 is people all know very well, the CO2 has fairly high vapor density compared with HFC, which is good for us since we can reduce pipe size, making the piping easier. But one drawback is if you have a high density in the coil with the same capacity, the velocity of the refrigerant in the coil get reduced. So say if you have the display, low temperature display case with the door during the night, the door is closed, the capacity is pretty low for the HFC, you still have a fairly good velocity in the tube to push the oil back. But if you retrofit it to CO2, then the velocity will go down even more. And during the night, it may trap some oil in the system. And in the morning, when you start to open the door, the capacity go back, then suddenly push a lot of oil back. So from this point of view, we would recommend, or we already see a lot of CO2 rack system have oil management subsystem installed. It come with oil separator, the oil management device, like I have shown here. It's
OMC,
kind of
yeah.
the oil, OMC, the oil level switch. But for different layout, it also requires slightly different design. Like for the left side, it usually good for the smaller system, like this condensing unit. If the coil is small, the oil, the possibility or amount of oil can be trapped in the coil is smaller. So we don't requires too big of volume for the oil separator. So this a fairly big oil separator is good enough to have a good oil separation efficiency and to store enough amount of oil in the system. But if for a larger system like a supermarket rack with tons of cases installed, then we require a larger volume of oil reservoir. In that case, oil separator may not be enough. So then we'll need to request to have an additional oil reservoir installed. And also, since in that system, we will have low temperature compressor and medium temperature compressor running, and usually the low temperature compressor cannot handle too high pressure. If you directly hook the low temperature compressor to the high pressure oil separator, it is a potential risk. When something's going wrong, you may overpressurize the low temperature pressure. So with an oil reservoir, you can run the oil reservoir to hook to the flush tank, have it running at a medium pressure, then reduce the risk.
Okay, because your low temperature compressor could be running at say 200 psi.
Yeah.
And then all of a sudden you'll be having 500 psi injecting in through the OMC. So the OMC open up, you got 500 psi. So that 300 psi differential is not a big deal for those.
Yeah, usually you have a way to overcome it. Either put an orifice inside of the line, or you have the level switch in the oil reservoir or oil separator to make sure there's only oil sent into the system, into the compressor. But if you directly hook the low temperature pressure to the discharge of the medium pressure, you hook 200 psi working device to let's say 1,200. Yeah, then it's become too big gap.
I even think the oil controls like the OMC, their differentials like 800 or 900, or I can't remember what it is, and I think most are. But I'll have to look into that differential because you're blasting 1,200 psi into that suction of 200. I don't know if that would be good, but have you tried that, Peter? Have you guys did a test like that at all?
You mean with the high pressure separator?
Into the low temp compressors.
Yeah, there are some risky things about this, and as I said at that moment, you really want to have enough discharge superheat not to have too much CO2 in the oil, because you are injecting it directly with a high pressure difference on
makes
the
sense.
oil system or oil management system, and then it really creates much wider foaming, and the level of the oil in the crankcase is really quite wild, and it can even increase the oil circulation if you do it too much.
Yeah, good, awesome. Yeah, love it, love this stuff. Learning so much. Hope everyone's taking notes, because I got a page.
Yeah, all right. So I think, yeah, that's it. That's all we have prepared for
Awesome.
today. And we
Okay,
already
I
5
do have
minutes
a couple
over the time.
questions, because I got a whole list of questions. I know we're 5 minutes over. I got this question a few times. So with CO2 compressors, if you're running really low compression ratio, is there a limit in that compression ratio? Because I was told, even when I worked at Copeland, you get that low 50 psi differential from your suction to discharge, that the reeds would start to flap, and it could cause issues with the reeds or potential pumping. Is there a limit on the compression ratio low end?
I would say that the limit is the best to translate into you need to have a certain compression ratio in order to increase the discharge temperature above the saturated vapor pressure, and that's the thing you should check.
Okay.
So actually, also if you are running with a very low pressure differential, you can have too much mass flow in the system, and it also loads a lot or your valving system, and there is also suction screen in the compressors, and it could happen that it breaks because of too big mass flow, because with the density of the CO2, even such things happen. But I think I would say that the best is to check really always that you have at least 20-30K discharge superheat, and then you are limiting the risk of too low compression ratio.
Yeah, that makes sense. Awesome. I love this stuff. I love talking about this stuff. There's so many more questions. I'm going to save these, and I'm going to ask you some of them later, send you an email. I want to thank you guys so much for taking the time to share your knowledge with us, because there's a lot to learn about. We do have one question in the chat that maybe we can get back to Henry on that, and we'll shoot him an email on that answer. But I really appreciate your time. I want to thank everyone for taking the time, hanging out with us. And where can people find you, or reach out to you if they want to get a hold of you or find out more about the Copeland compressor product line?
There is a lot of papers, a lot of material on the website of Emerson, and there are even several locations. There is this super nice E360 hub, which Andre Patenot is very active in, and you can find a lot of videos and presentations. And I think that, and as you always said, it's always important to read the manuals, and I think those are also very good, both in Europe and North America, and they are also available on the Emerson website. And you can see our email addresses here, so do feel free to reach out to us if you have any questions later on. And I think that's it. And I want to say thank you, and it was a real pleasure to be here with both of you and the team online. So it was fun. Thank you.
Yeah, no, I really appreciate it. So e360hub.emerson.com is where you can find a bunch of information, and yeah, reach out to me as well if anyone wants to get in contact with Joe or Peter. Joe, Peter, thank you so much, and we'll see you at the next CO2 Mondays. See you, everyone.
Thank you. Thank you, everyone.
See you later. Bye.
Hey, I want to thank you for taking the time to watch this video. I hope you got something out of it, something that you can use in your daily life. If you like this video, hit the thumbs up button, hit the subscribe button, and click the bell button, because
When you click the bell button, it will notify you anytime new videos are released. Also, check out the Refrigeration Mentor webpage at refrigerationmentor.com, where I'll have all the different trainings, upcoming events, the different podcasts I've been on, as well as the Refrigeration Mentor podcast. If you want to check that out on Apple, Spotify, Google, any service provider of your choice. Super excited to see you at the next video. Now let's get a conversation going.